Okay, so maybe we can start. So welcome everyone to this set of lectures on, I guess, long-range statistical physics of long-range quantum systems. So Nicolo Defenu from ETH Zurich will tell us about this. So Nicolo, you can start.
Okay, thank you very much for the introduction, Abhishek, and thank you everyone for attending. I'm very glad to be here, even if only in online format. I would have been very happy to come in person to Bangalore, but this period of the year, my son was recently born, and it was impossible for me to travel. But I hope that in this, even if this online format will not be the best for discussion, it will still be able to. We can use some other upwards of the online format and have and use the slides in a proper way. Okay, so this lectures that I'm gonna give, it's built on it's supposed to build and extend what Stefano Russo has been telling you this week about long-range interactions in classical systems, and we are gonna move it to the quantum world. And so part of this first lecture will be devoted to justify what is our interest in long-range interaction in the quantum world. So why is this important? Please feel free to interrupt me and ask questions if you need to do so. I cannot see the audience, unfortunately, while I'm speaking, but I trust the organizers to tell me if there is questions, or you can also just speak up.
Yeah.
Okay, so perfect. So let's start, as I said, with some motivation. So the motivation, so the reason why long-range interacting systems have been subject to an increasing amount of interest in the recent years in the world of quantum many-body physics is that at present there are different and multiple platforms that are able to perform quantum simulations with long-range interactions. So this is something that's, in some sense, it's even better. So it improves, if we want to call this an improvement, but it's radically different from what happens in classical physics. So in classical physics, long-range interactions occur naturally in some systems, like gravitational systems or plasmas. But these natural long-range interactions, they cannot be controlled. So most of the discussion of long-range interaction in classical systems, it's about simplified theoretical models. So the models that have fully connected interactions, that are the one that Stefanos, I believe, has been talking about this week, in the classical world are in most of the case just some approximation or some theoretical tool to understand more or less what's going to happen in a long-range interacting system. But in the quantum world, the situation is different. So long-range interactions, the type of long-range interaction I'm going to focus on is the one in which one has a system that's done of multiple components, and these components that can be atoms or more often spins, they interact via a two-body potential, and this two-body interaction potential decays as a power law of the distance between the components. And I'm not gonna, and I will try as much as possible during the lecture to talk about the general case alpha, so where the power law exponent of this decay potential, this 1 over r to the alpha, where the alpha can be tuned. But this is going to be mostly in the second lecture. So in the lecture of today, we are going to focus in the case where alpha is pretty small, smaller than the dimension of the system. And basically, it's close to the case that Stefan has been discussing during the week of alpha equal to 0. But as I say, that in the world of quantum physics, we can realize all alphas, because we have quantum simulation platforms like the one that you see represented in these figures, which are able to simulate different values of alpha, and sometimes all of them, as is the case of trapped ions. So you see trapped ion systems, which are represented by this figure in here, are systems that are made of ions. So the black dots in the sketch are ions, which are arranged on a Wigner crystal. And the interaction between these ions are mediated by the phonons of the crystals. And this interaction, they have a power law exponent alpha. I'm sorry, in the picture, the alpha is called an A, but it's A and alpha are the same in the slide. So the interaction, the power law decay alpha can be tuned from 0 to 3 in 2 dimensions. That's a pretty impressive range. And the same can be done in 1 dimension. So this is achieved basically via trapping the ions in a pending trap. So you see the ions are trapped and confined in 2 dimensions by this kind of trap where the ions are electrically charged. So they can be confined by an electric potentials. Since they are very cold, they arrange themselves naturally in a crystal. And then you can tune the frequency, the dispersion relation of the phonons in the crystal by some RF fields that are represented by this, no? And the angle and the characteristics, like the frequency of these RF fields, they are capable to modify the dispersion relation of the phonons. The phonons modes are represented by this Bi and Bj. They can modify the dispersion of this phonon mode in such a way that the coupling, this Jij, there's the coupling between the ions. The internal level of the ions represent effectively a spin system. So this can be seen as 1/2 spins. The coupling between these ions decays as a power law. When we change the ratio between omega r and omega r plus mu r, we can see we can tune different kind of interactions range. So this is a kind of system that in the quantum world, so the ions are very cold, so quantum effects are relevant in the system, is able to generate long-range interactions with a tunable decay exponent alpha. But for the sake of this lecture, of the present lecture, it's even interesting to talk about this second type of experiment, which is an experiment where only one value of alpha can be simulated, but it's the one that you have been probably discussing the most this week, which is alpha equal to 0. So alpha equal to 0 is the case of a fully connected interaction that does not decay with the distance. And in this way, and this can be realized by an ensemble of a condensate of atoms trapped inside the mirror of an optical resonator. So I want to give you some details because this is a very important experimental devices. If you consider how much you have been discussing the case of the Hamiltonian mean field model and the fully connected interactions, it's important that you see that in the quantum world, we can really realize this kind of interactions. And we do it in a simple way. So we take this cavity system, and the cavity system is a single mode cavity. So it can be represented by a single photonic mode. So the Hamiltonian is just a simple bosonic operator. And the Hamiltonian is detuned, and this delta is the difference between the frequency of the mode in the cavity and the frequency of an external laser field that pumps the cavity from the transverse direction. So these purple arrows. So this is the detuning. And so this Hamiltonian is represented in the so-called rotating wave approximation with respect to the pump field. Then we have the Hamiltonian of the atoms. The atoms are in a condensate state and they are trapped into the resonator, and the Hamiltonian is the standard one of interacting particles. So there is a momentum contribution p squared over 2m. There is an interaction part, local interaction between the atoms, but there is also the coupling between the atoms and the potential which is generated by the pump field, which is this one. So you see the potential generated by the pump field, it depends on the characteristic function of the pump, but all of these details will be washed away in a few slides. Finally, the third contribution to the total Hamiltonian of the system is the interaction between the atom and the cavity. An interaction between the atom and the cavity is pretty simple, because basically the atom can scatter the photons in the cavity mode. So the cavity mode is the operator A. So you see there can be a scattering between the atom and the cavity field. This scattering has a form factor that depends on the pump mode, on the cavity mode, but as I say, these details are not so important. And then we have also to consider the fact that there is some shift to the atomic level due to the density of light in the cavity, which is this part in here. What's the process that's interesting for us? The process that's interesting for us is the scattering of a photon from the pump field with an atom, which generates a photon in the cavity and then again in the pump. So this is the scattering process that are interesting for us, because the cavity is longitudinal, but the pump is transverse. So if the cavity were empty, there will be no photons in the cavity. But due to the fact that in the cavity one has atoms, so there can be a scattering of the pump photon into the cavity and back into the pump. This scattering process is a two atom process, and it's exactly the one that's sketched in this plot. The pump photon comes, it scatters with the atom. The atom acquires a momentum, which is partially longitudinal with the pump, but also partially in the direction of the cavity. And as a result, the new photon that's scattered from the atom has a momentum that's transverse with the cavity. So this is resonant with cavity mode. Then this photon can interact with another different atom through this interaction that you see here. And the result is that the final photon is again longitudinal to the cavity, to the pump field, and the other atom is also scattered with a different and opposite momentum from the first one. So since the atoms are in a condensate state, in absence of the pump field, they are mostly in the zero momentum state. And so the initial state of this scattering process is the two atoms in zero momentum, and the final states is atoms which have momenta in opposite directions, like this. Okay, the momenta are a little bit different because the first scattering is with a pump photon and the second scattering is with a cavity photon. But please consider that this delta C is the tuning between the cavity and the pump has to be small in some sense. So this delta C is small, and so the difference between these two momenta is pretty small, and we can also take them equal. And that's what we're going to do in the future. So this is the configuration, and it should not be hard for you to understand from what I've said that the scattering between the photons of the cavity and the pump with the atoms generate an effective interaction between the atoms, no? Because the photon of the pump scatters the first atom and then generates a cavity photon that scatters with the second atom, and this generates an interaction, effectively couples the two atoms. This kind of interaction, it's not surprising that it doesn't have any range because the cavity photon are standing waves. They don't have any decay. Their mode function doesn't have any decay. But in order to see that, there is a little bit of a formal way. I am not going to give you the details of this calculation. You can do it if you wish. It's you can find it in the reference that I have sent you before the lectures. So this reference in here, archive 2109. So this is a review by myself and collaborators, and everything that I'm saying here can be found in the review. And if it's not on the review, you can find in the review a lot of reference that will discuss what I'm saying. So basically, what you can do to show that this process generates an effective interaction between the atoms, you can integrate out the cavity field. So what it means, integrate out, it means that we have this Hamiltonian and we eliminate from the Hamiltonian the a dagger contribution by solving them in some perturbative manner, as I said, integrating them away if you are familiar with the path integral formalism. So obviously this procedure is approximate and it's valid only when the cavity modes are fast. What it means fast? So the cavity has a dissipation. So you see from this plot, there is the pump of the cavity, there are the atoms inside the cavity, but there is also some leaking of the cavity photons out from the cavity. And this number has to be large with respect to the average kinetic energy, the characteristic kinetic energy of the atoms. The characteristic kinetic energy of the atoms is the one that results from these processes of order K. As I say, Kc and Kp are both the same, and I'm going to call them K in the future. So when this is true, it means that basically the photon in the pump, they can only scatter one atom before being lost. And so it means that quantum correlations of the cavity photons are not so important, and we can just integrate them out at first order, and we get an effective interaction between the atoms. And then what's represented here? So we have an effective Hamiltonian where the cavity modes has been completely removed, and we are only left with the Hamiltonian of the atom plus an effective interaction between the atoms themselves. And this new interaction is long range because it's the result of the convolution between the pump field and the cavity field. This is not surprising if you think about this process. But when you go and you look at this in a real experiment, you will see that this is basically proportional to cos kx, cos ky. And so this is an interaction that does not decay with the distance. Okay, it's an interaction that basically it's all to all. Well, but why it's all to all? Well, it's all to all because what happens is that there is a transition. So when you look at this in this way, you wouldn't say it's all to all because it's a cosine. But this cosine, so it's a cosine where the x is the position of the atoms. The position x is this and y is this. So x is the position of the atom on the x-axis. And k is the wave vector of the standing mode of the cavity. So, but the atoms are attracted, so they want to fall into the places where the cavity has light. So this is exactly the transition that's represented here. So there is an order parameter for this model. And the order parameter is basically the number of atoms which occupy the minima, or sorry, the maxima of this standing wave cavity field. And so we can kind of represent it like as this can be, you can represent the order parameter in this way, no? It's the sum of cos k x j, sum over all atoms. So this k, the position of the atom j. Each time this is basically a multiple of 2 pi, this is a 1, and the order parameter is maximum when these guys, they all occupy the maxima of the standing wave laser field. I'm sorry, of the standing wave cavity field. So we have this process. When the cavity is pumped with a too weak intensity, nothing happens. There is some scattering of light in the cavity, but this process is not strong enough. And the atoms basically remain in a condensate that is a little bit perturbed by this pump field that acts somehow as a small effective temperature. But as we increase the pump strength, what happens is that there's going to be a massive amount of photons in the cavity that will generate an intensity of lights in the cavity. And this intensity, and then the atoms, they want to occupy the maxima, or depending on the atom, it can be the maximum or the minimum, but let's say in this case, the maxima of this standing wave. And this is exactly what is represented here. So for big enough pump strength, the atoms occupy the maxima of the cavity intensity, of the cavity field intensity. And so they basically they form a structure, a crystal, ordered state. And in this ordered state, the interaction that you see here, they really are fully connected. They don't depend on the position anymore, because all of the atoms, they only live on the maxima of this cavity field, and on the maxima, this cosine always evaluates to the same point. And so we have an interaction that's all-to-all and independent of the position. So if you kind of get a glimpse of what I'm saying, you won't be surprised if I say that this situation, this kind of transition, can be effectively represented by an Hamiltonian mean field model. The Hamiltonian mean field model is what Stefano has been discussing during the last week in classical system. In classical system, it represents a theoretical model, a simplified fundamental model. But here in Cold Atoms into Cavity, we can realize it. And we can realize it because when we describe this phenomenon of the phase transition, of this super-radiant transition of the atoms in the cavity, and we look at the effective Hamiltonian in here only in terms of the order parameter, it really looks like the Hamiltonian mean field model. So there is the momentum of the particle plus a global interaction term, and the global interaction term, which is this one, it can basically be represented as order parameter to the square. And so you can read it in this way, and you can see this looks much alike the Hamiltonian mean field model. Much, much, much alike. The only difference, so we have in both of the system, we have the cat scaling. That's interesting. We have the cat scaling basically because the interactions as mediated in here, it basically it decreases when the number of photons in the cavity increase. That's an effect that you can see if you see the calculation. So the cat scaling is automatically implemented in this cavity setting. The interaction of our global interaction, so they don't decay with the distance. This is the reason, this is what we have said before. It's very close to what happens in an Hamiltonian mean field model. The particle move on a ring, the interaction are cosines, but in the, let's say in the low temperature phase or in the crystal phase, they are all at the minima of these cosines, and so they have a fully connected all-to-all coupling.
One question.
Yeah, of course.
So you got this effective model for the wave function psi, like there's some effective Hamiltonian after integrating out the cavity mode.
Yes.
What are these? So thetas are the phase of that wave function, or so I didn't understand the how you got from the complex wave function to this.
So basically, well, I'm working in a second quantization setting, so I'm not talking about wave functions. I'm rather talking about operators. So these are accretion and dilation operators. I didn't give you much of the details how I got from here to there, but the point is the following. So you have this starting point. You have the starting point is the Hamiltonians of the atoms coupled to the cavity field. No? So the starting Hamiltonian is the one of the cavity, a single mode photonic Hamiltonian. The one of the atoms, which interact within themselves and with an external potential that's given by the pump. And the third contribution of the Hamiltonian is the coupling between the atoms that are in the cavity and the cavity field. Okay, do you see that there is this contribution, no? So this contribution represents the scattering process I was talking about. A photon of the pump hits an atom, it scatters a photon into the cavity, and then the photon of the cavity is scattered by another atom. So this process is represented by this interaction Hamiltonian. Okay. Now you are right that in this Hamiltonian, this model as is written here is not so close to the standard Hamiltonian mean field model I will introduce later. But what I can do, I can just basically, for example, so when I say I can integrate out the cavity field, I don't know if you are familiar with this procedure of integrating out a field to obtain an effective Hamiltonian. But basically what I'm doing is I am taking, for example, this Hamiltonian, the interaction part, and I'm treating it in some kind of perturbation theory. Okay? But in this perturbation theory, I don't try to solve for the fermionic operators. I only try to basically treat in perturbation theory the photon mode of the cavity. So this is some kind of semi-classical approximation in which I'm saying, okay, the atoms are quantum, but the cavity field is not. You see what I'm trying to do? So in this slide, everything is quantum. In the second slide,
I mean, so this is clear that you integrate out the cavity field and get some effective Hamiltonian for the electrons, right? Which in the whatever second quantized notation. But after, so till that it's clear. And then how do you go make the connection to the classical model where thetas are the degrees of freedom?
Basically, okay. So also that is still a semi-classical approximation, basically. So the semi-classical approximation that I do is that I know that this interaction depends on the, so if you are right, this is a little bit switching between notation because here it's in the second quantized notation, but here somehow I go to the first quantized notation where this xj is still an operator and its operator is the position of the atom. Okay. So I define this order parameter. This is just a definition. So this is an operator. It counts how many atoms are in a position which is resonant with the maximum of the cavity. And when I write this in this way, I can represent this interaction potential, that's cos kx, cos ky, as theta to the square. So these guys, so this is still operators. These two Hamiltonians are kind of the same. So the p square part is hidden in here. And this part here, I have only switched from a second quantized notation to a first quantized one, where these guys are operators. And they count, they tell you, this is the position of this is the position of the atom I, this is the position of the atom J, this is the position of the atom I, this is the position of the atom J. So here I've done just simple algebra, basically. But I have switched from a second quantized to a first quantized form. So this model is still quantum. Okay, sorry. I should have put heads on operators. But then when I treat this quantum model in the semi-classical way, then it's really the Hamiltonian field model. And otherwise, a quantum version of it gets much more complicated, okay? But here I wanted to convey you that it's the same physics, because the Hamiltonian is the same. Here, these are operators, you are right. These are classical variables. But when I treat this Hamiltonian at semi-classical level, so when I discard the fact that they are operators and they treat them as classical variables, then the two systems, they describe the same phenomenology. And one is just the quantum version of the other.
Okay.
And they all have the same features, but the fact that this Hamiltonian of the cavity, it has a translational symmetry breaking term, this cosine kx plus ky. So the Hamiltonian midfield model is perfectly translational invariant. This one is not. But okay. In some sense, this is not so important because if the cavity is big enough, so basically you can show that this in certain approximation, this can be disregarded to a certain extent. Very good. So basically, I hope I at least convinced you or give you a glimpse that in this cold atoms into cavity setting, we can realize an Hamiltonian midfield model. It's a quantum version, but at the semi-classical level, they give the same result. They are systems with global interaction that describe a second order phase transition. In the case of the Hamiltonian midfield model, the second order phase transition is to a classical crystal phase. And even in here, it's a transition to a crystal phase, but people call this a super radiant phase. And it's a super radiant phase because when the atoms occupy these nodes of the cavity field, so the maximum of the cavity field, they also maximize the scattering of pumped photons into the cavity. So you see, this is what happens. So they maximize this kind of scattering. And if they maximize this kind of scattering, there is also a lot of light leaking out of the cavity. So this is a lasing transition. It's not an efficient laser because you have to pump it with another laser, but okay, it's still a laser in a sense. You have some matter, you pump it with a laser field in a certain direction, and you get as a result a lasing field on the other direction. So this is kind of a lasing transition. But it has all of the features at semi-classical level. It has all of the features of the Hamiltonian field model. Very good. Okay, so I hope I convinced you that it's interesting and important to talk about fully connected global interactions in the quantum world. So in the quantum world, we have fully connected interactions. We can realize them. And I showed you where you can do that. Now I'm going to study a model which is somehow a simplification of the one I was talking about. That's not going to talk about atoms anymore. It talks about spins. It's still a good model to describe this transition only when you approach the transition from the lasing part, no? Because in this configuration, in the configuration when the pump field is strong, the atoms are basically froze in the maxima of the cavity field. And the only interaction that occurs is interaction between internal degrees of freedom of the atom. So you can use this to represent an Ising model with fully connected interactions. So as long as you consider this system in the lasing phase, you can kind of see that this realizes a fully connected system with spin degrees of freedom. Sorry, I said that the spin degrees of freedom is the internal state of the atom. So this is a way, but you can also encode the spin degrees of freedom into these two states, the 0, 0, and the symmetric combination of these states in here. So this is also a possible way to encode the spin variable into the atoms. However, let's not spend too much time on these experimental details. I'm just saying that the experiment I was talking about before, it can be described effectively by a quantum Hamiltonian field model, but it can also be represented in the laser phase. It can also be represented as a fully connected spin Hamiltonian. And a fully connected spin Hamiltonian is exactly the one that I'm representing here, which is a fully connected Ising model in a transverse field, or some people call it a Lipkin-Meshkov model. I don't know how many of you are familiar with this notation. Let me try to briefly remind it to you. The spins, the sigma z and sigma x operators, they can be represented as Pauli matrices, and they are, or basically 1/2 Pauli matrices, and they act on a two-dimensional Hilbert space. Well, they are Pauli matrices. And basically, this is the Z component, is the standard classical spin that you are used to. It's 1/2 minus 1/2, while the X component represents an operator that allows the spin to tunnel from up to down. And this Hamiltonian is the kind of workhorse of quantum phase transitions. Because this Hamiltonian is the Hamiltonian of spins that have a ferromagnetic interaction between their Z direction. And so this would be the classical Ising model if there were no this part. Because when you add the transverse field, you cannot consider this Hamiltonian classical anymore because the operator sigma z and the operator sigma x do not commute. Once again, they're Pauli matrices. And there is a competition between the sigma x transverse field that wants to spin to align to the transverse field, and this sigma z that wants the spins to be aligned between each other in the Z direction. So there is a quantum phase transition. The quantum phase transition occurs obviously at 0 temperature, and at 0 temperature, the quantum phase transition occurs when at a certain critical field H, for H critical, HC. When H is larger than HC, the model is in paramagnetic phase. This contribution wins, and the spins are mostly aligned with the external field. When the H is below the critical value, this ferromagnetic interaction wins and all the spins are ferromagnetically oriented around Z. We want to see how to describe this transition in the version of the model where there are fully connected interactions. So in the version of the model that is written here, where each spin interacts with each other spin. And in order to describe this, also in the quantum world, we will use the kind of same approach that we normally use in the classical world. So we want to compute the partition function of the system. We want to make the trace of this exponential of minus beta h. So this is the Boltzmann weight of the system, and we want to trace over all possible states. Now the difficulty is that this is an Hilbert, so we have to trace over the Hilbert space of this system, which is very, very large, because there is an extensive number of spins, and so the Hilbert space is exponentially large. But since the interactions are fully connected, we can kind of simplify the situation, because it's true that this looks like a many-body Hamiltonian, because there are an extensive number of spins. There are spins there's a spin on each side of a lattice. Sorry, I didn't say that I am considering a one-dimensional system, no? So obviously the dimension of the system is not so important when I have fully connected interaction, but just for concreteness, I am considering a one-dimensional systems where there is a one-dimensional chain of sides, and on each side of the chain, there is a spin, a sigma. So it's true that this is a many-body system because I have a lattice with many spins. But when I look at the Hamiltonian, I can rewrite it in terms of a global variable. And the global variable, I define it in this way. I define the longitudinal magnetization mz, this one. I define also the longitudinal magnetization my, that's the sum over all y components of these spins. And I define the transverse magnetization mx. All of them are defined in the same way with just different coordinates. Now I can represent the Hamiltonian of the system only in terms of these global operators. So you see, from the point of view of many-body physics, this is not really a many-body system. This is a single spin. It's a single giant spin in the sense that the spin is of the same side. The sides of the spin is the same as the system side. So how many sides I have in my lattice, this is the length of the spin. But the Hamiltonian can be written only in terms of this global coordinate. And so it just represents a Hamiltonian of a single giant spin with a self-interaction term. So if it is a single spin, we can use the standard quantization number for quantum spins. And the standard quantization numbers are the S square, so the modulus square of the spin, which is conserved by this Hamiltonian, so it's a good quantum number. And the second quantization number that we are going to use is the magnetization along Z. But this is just the one we want to use because we want to make the parallel with the classical Ising model, which is magnetizing along Z. And so we have these two quantum numbers. There is a standard situation of a spin system, the S square, when there are coherent states, which are characterized by the two quantum numbers. And these are the result of acting with the two operators S square and MZ on these coherent states. Now we can use the coherent states to try and carry out this calculation. So we want to do the trace, so sum over all possible states, this operator, the Boltzmann weight. And what we do is, first of all, we split the Hamiltonian into slices by using what is called a Suzuki-Trotter transformation. So a Suzuki-Trotter transformation is based on this simple equation, which the exponential of the sum of many operators is equal to the limit of the product of the exponentials. So for classical variable, this would be true for any ns, not just at ns equal to infinity, but for quantum variables, so where a are operators, this only becomes true in the limit where ns goes to infinity. So we do this procedure on our Hamiltonian. We split the Hamiltonian into slices. We make NS replicas of the Hamiltonian. So you see, the difference is that in this exponential, we have the non-commuting terms together, but now we can split them thanks to this formula. So we can split them because, as I say, the fact that they are non-commuting is not relevant when ns goes to infinity. The non-commuting operators are not relevant when ns goes to infinity. And so we can use this procedure and split the Hamiltonian into two terms, actually into many terms, but each of these many terms is split into two subterms, one term only as mz and the other terms only as mx. Having done that, we sandwich into each of these slices a completeness condition. The completeness condition is that a sum over all states in the Hilbert space. And we know how to parameterize these states because these states now are just the coherent states that I defined before in terms of the global variable. So we have a good basis to do that. The good basis is the one of the coherent states. So we put this completeness condition for each slice and we get to an equation like this. This seems very complicated, I understand, but please stay with me for a while. It's not so hard. The partition function is just the exponential of the Hamiltonian. It has been sliced. The slices are labeled by alpha, and alpha goes to 1 from 1 to ns. That's the number of slices, of course. And for each of these slices, we have inserted a summation over all possible states of that slice. Okay, so we basically took a system and make infinite copies. Each of these copies is a slice in the Trotter space. The only thing, the simplification occurs because on each of these slices, we are allowed not to consider the non-commuting, the fact that the operators in the Hamiltonian do not commute. So for each single slice, we can split the exponential into the product of two exponentials. But we can only do that because we have infinitely many slices, only in the limit ns going to infinity. But okay, so that's what we have done. And so now the things has become a little bit simpler because we know how mz acts on these states. This is easy because these coherent states are eigenstates of mz. And the only thing that remains is this mx. And the mx allows the Trotter slice to turn, so it couples different slices. So I took my system, which was a one-dimensional system. I made infinitely many copies of it, which are the Trotter slices. But now there is still a coupling between the Trotter slices, but this coupling is nearest neighbor because it's given by mx. And this mx is only able to flip the spins, is only able to increase the mz by 1. And so basically it's only able to tunnel between nearest neighbor Trotter slices. Okay, so this is what happens. So the situation is kind of simplified because we don't have to take into account the fact that the operators do not commute, and we know how mz acts on the coherent states. And we also know that mx is local between the slices, so it only couples nearest neighbor Trotter slices. But we can still do something to simplify the thing even more. And what we do is that basically we, sorry, there's a question. Okay, seems there is no question. So what we can do is can basically introduce an order parameter, which we call m alpha, and m alpha is nothing but the expectation values of mz. So it's, you see, remember that mz, as written in this, it has a hat, it's an operator. But m alpha is the expectation value of that operator, because it's the sum over the value of the sigma z on the Trotter slice, and these are classical variables. These are classical, they are eigenvalues of the coherent states. So basically, we can introduce this. Expectation value, and we introduce a delta function to fix the expectation value. Sorry, guys. Sorry for just. Okay, sorry. So basically, we introduce this delta function, and this delta function. Sorry.
Nicolo, I mean, I don't know if you're using your pointer because we can't see the pointer.
Can you? Sorry, you can see it.
No.
Oh, you're right. That is. Oh, okay. So, just a moment.
Yeah, now it's there.
It's there.
Yeah, now it's okay.
Okay, sorry, I could see it, but I don't know why you cannot see it. But now you should be able to see it.
Thanks.
Maybe. Well, okay, I cannot get rid of this upper thing, but it doesn't matter. Then what I was saying. Okay, so we take this. So the point I want to make is that we want to introduce this order parameter. Now it's a classical variable, and we only have to make it in such a way that we are sure that the classical variable, it represents, so we are sure that this equation is satisfied at each slice. So for each of these subsystem I have split my system in, we have to ensure that this equation is fulfilled. We have to ensure that this equation is fulfilled. And this is what we do in this part. So we take this expression of before, and we substitute to this operator its classical, the order parameter, its classical expectation. And then we have to introduce this Lagrange multiplier, lambda alpha, in such a way that when we introduce the Lagrange multiplier, integrating over the Lagrange multipliers, it gives us the delta function. So it gives us the insurance that this equation is fulfilled. So when you integrate on delta lambda alone, you will get that we will get a delta function of m minus this sum. And you can see it here because the lambda occurs both in here that multiplies m alpha, but in here where multiplies sigma z. And so you can basically see that when you integrate over lambda alpha, you get this delta function that ensures that this equation is fulfilled. The delta function of m alpha minus some sum over sigma z alpha. Okay, so basically this is what we have done. So what is what we should do? I am not doing the calculation in full details. You can check all of it in this very nice reference by Babs and Semerjan. I want to just give you a glimpse of how we can treat fully connected systems. So for fully connected system, we can do this trick basically. We can go into Trotter space. And then we can substitute our operators with classical variables thanks to the fact that they are global operators. So you see, I wouldn't be able to do this if this were a local system, because then I will have a coupling that is local on each side. But since it's a global operator, I can just introduce its classical variable. So basically in this way, I have just to introduce a single constraint for each Trotter slice. And so this is quite convenient because now I don't have any more interactions in the quantum world. Now my quantum operators are single operators. You see, this is a single side operator, sigma z and sigma x. These are 2 by 2 operators. And this simplification has occurred because I took my global variable, the mz operator, and I made it classical by this simple trick. Okay, now basically all the quantum nature of the system, it's hidden just in this simple trace over a 2x2 Hilbert space. So this is quite a lot of gain. We can do this summation explicitly, and we get to this result. So this is the free energy of the system. The free energy is just the logarithm. Sorry, here I'm missing an equal. Okay, so basically, this when we take the logarithm of this quantity, we just obtain this quantity here. And this is very simple. And even if I haven't done the calculation in full glory, you can immediately see that this is the true result, because this is just, oh, sorry, this is just this, when I take the logarithm, this is just the exponent that I get off, because this integral basically simplifies. The only part that you don't see is when I do the trace of this guy, but the trace of this guy is the one that gives me this hyperbolic cosine, this log of 2 hyperbolic cosine. So basically, this is the free energy of the system. And in order to obtain the free energy of the system, I have to do the minimum with respect to m and the extremum with respect to lambda. And this minimum and the extremum, they turn out in the thermodynamic limit because I have the n. So this is the way in which I have done the integration. I have taken this guy in the limit n to infinity, and in the limit n to infinity, only the saddle point matters. And so basically, I don't have to do the integral anymore. I can just consider the saddle point, so only the exponent calculated at its minimum gives me the entire contribution. And when I do this explicitly, I get that the free energy is the minimum and the extremum with respect to lambda of this expression here. This is very simple calculations that you can all do at home if you wish. Something very simple. And when you do it explicitly, you will find that this in order for this minimum and extremum condition to be satisfied, these are the equations that you take. Lambda is equal to 2jm. So this parameter lambda that I had introduced in order to keep track of my definition of the classical interparameter, it's just the same as the magnetization in the thermodynamic limit. So in the thermodynamic limit, everything simplifies because of this n which is in front of here. And this is again something that comes from fully connected interactions. So this lambda is equal to 2jm, and the magnetization m is just given by these equations. And when you plug this equation into this equation, you get a self-consistent equation for m as a function of n. It is the standard mean field result for the solution of the model. Basically, by this procedure that may look a bit complicated, we have found out that in thermodynamic limit, the solution of the fully connected quantum system is exactly given by the mean field, because this is a mean field equation. You see, the magnetization is obtained as an hyperbolic tangent of the magnetization itself, because lambda is the magnetization. And if you want, you can also do the full quantum limit, that is the limit t equal to 0. So beta goes to infinity, and then this hyperbolic tangent simplifies, and you remain only with the condition m is equal to m over square root of m squared plus h squared, which is the mean field condition of the quantum system. So basically, nothing much has happened. We can now plot the magnetization mz. So m is the magnetization along z. So in the plot, I call it mz, as a function of j at a fixed h, or you can do the reverse, it gives the same plot basically. So if you fix h and you plot it as a function of j, you will find exactly what you expect to happen. Depending on the temperature, you have a certain critical j, and at the critical j, the magnetization starts to rise up. And at temperature equal to 0, the critical j is h half. So it's 1/2 of the magnetic field, which is correct because we know that the critical h will be 2j for the mean field approximation. So it's the same. And so you see that this is all of this. It was just to say that the fully connected system is solved by a mean field condition, is exactly solved by the mean field condition, because in the thermodynamic limit, this saddle point is exact because n appears in here. And you see that you recover what you expect from a second order phase transition. The magnetization is 0 for several j's, and then it starts growing up at a certain j critical. You see that in this kind of system, there is not much difference between what happens at finite temperature and at 0 temperature. And this somehow a little bit, it can seem a little bit surprising, but what you can see in this system, you can also try to look at the thermal phase transition. So there is also a thermal phase transition as a function of the temperature. The temperature is here. It occurs in the same way as it occurs in the standard classical Ising model, because this is the same mean field condition. And as you see, if you try to plot the critical temperature as a function of j, you will see that this is the plot that you get. So you have a critical temperature that depends on j, and all of these, so all of these critical temperatures, they represent a second order transition between the paramagnetic and the ferromagnetic state. So both at t different from 0, so there is a thermal phase transition with a critical temperature Tc, and there is a quantum phase transition that occurs at t equals 0 as a function of j or h, depends on what you want. So you have both these features in this model. At finite temperature, the equation, when beta is finite, this equation looks very similarly. It's not exactly like the one of the classical Ising model. There is only a small contribution from the quantum fluctuation, that this is h squared, but it doesn't change the physics. And at 0 temperature, you get an equation that gives you the magnetization as a function of j at finite h at t equals 0. So this model both describe thermal phase transition and quantum phase transition in the same way. And this may be a little bit surprising for you, because normally people are used to think about quantum critical behavior and classical critical behavior as two different things, as two things that are, so the classical critical behavior is something that occurs at finite temperature, and the quantum critical behavior is something that occurs at 0 temperature as a function of some parameter p. And so here I show you the standard plot that you will find in the Sachdev book, Quantum Phase Transition by Subir Sachdev. And if you haven't read this book, please have a look to it. It's a very interesting book and nice book which describes quantum phase transition. And I want just to tell you that this plot that I think everybody knows, that displays how a classical phase transition becomes a quantum phase transition in the 0 temperature limit, is exactly this plot here. So this is exactly what this model is able to describe. So as a function of some parameter j, which Sachdev calls p, because he wants to be generic, but for us, it's the ferromagnetic interaction of the quantum model. As a function of j, you have a family of thermal phase transition. And this family of thermal phase transitions, it ends up at Tc equal to 0, where you have a quantum phase transition. and this is exactly what is described also in this plot. So basically nothing. I wanted to show you that this model is really fundamental, and it encodes all of what we know about the interplay between thermal phase transition and quantum phase transitions. You have been talking during this week a lot about the classical phase transition as a function of the temperature in the HMF and in the Ising model and in this kind of spin systems. And I wanted to show you how all of this is connected and is present also in here, also in the quantum world, because in the quantum world, we can consider a simple quantum version of the Ising model with fully connected interaction. We can solve it explicitly by Suzuki-Trotter decomposition and saddle point approximation. And this solution is of a mean field type. And as a function of beta, the inverse temperature, and J, the ferromagnetic coupling, we recover exactly the picture that we expect with a ferromagnetic phase, a paramagnetic phase, and a family of second order transition, a finite temperature that ends on a quantum phase transition of second order at 0 temperature. Are there questions up to now? Because now we are going to a little bit switch and change to not a different topic, but something. This is the more like fundamental part of the talk.
So I mean, so for this mean field quantum Hamiltonian, is the spectrum sort of known exactly?
Okay, so basically you don't know the spectrum exactly. What it's sorry, I don't know why my computer has decided to switch up and down now, but this doesn't matter. So the spectrum is not known exactly, but what it's interesting is that you can write some differential equation. And so basically, okay, so let me say it like this. From this approximation, so this is a saddle point approximation that gives you only the ground state, no? So this is the ground state solution. And it shows that the ground state has a symmetry breaking procedure. And from the point of view of this calculation, it's evident that this quantum system becomes classical in the thermodynamic limit, no? Because it's evident that when n goes to infinity, the saddle point approximation becomes exact. And so basically, the systems behaves as a classical one, because quantum fluctuations are, they have to be accounted by this integration, but the integration becomes unnecessary in the thermodynamic limit. If you ask about the spectrum, you are kind of asking something more than this calculation can give, because you are asking not just about the ground state, but about the different levels. But if you go into this paper, they will show you how can you obtain the spectrum of the system in an expansion as a function of n, obviously. So you can do corrections in 1 over n to this calculation that I have made, and you can obtain the spectrum of the system by a differential equation. So basically, you can obtain the spectrum of the quantum system just by solving the spectrum of a single differential equation. And this kind of tells you that the analogy between the classical and quantum that I have shown you for the ground state, it also holds for the spectrum, because you can obtain the spectrum of the quantum system just by solving a differential equation. However, this spectrum is only known to, so it's just an approximation in powers of 1 over n, if you know what I mean. No, so it's, you don't know, you never know the full spectrum. You just know 1 over n corrections to it. Does this answer your question?
Yeah, so I mean, yeah, sort of, but even though it looked like once you write it in terms of this m variable, it looks like a single particle with a large spin, right? Mz square plus mx. So it looks like a simple Hamiltonian, but still it's, you can only find the ground state exactly. That's what.
Yeah, exactly. So basically, well, in some sense, when you go into the thermodynamic limit, you can only find you can also only work in 1 over n expansion. So okay. If you want to know things exactly, you have to expand around the thermodynamic limit, because you don't know. So because the Hamiltonian is simple, but when n is finite, it's not known, sorry. So it's not known what's the spectrum of this Hamiltonian for a finite, any finite n.
Okay.
So you can only work with small n, okay, then you count it explicitly, or around infinite n, you can do some approximation at 1/n. So infinite n, you just have the ground state, finite n, you see some corrections, and you can build up corrections at finite 1/n. But you don't know the spectrum for exactly the spectrum for every n. Actually, it's kind of complicated.
Okay. So the other question was, I mean, like in the classical case, there is this question of like what we saw is there is this inequivalence of ensembles and so on. So does one also expect similar stuff here? I mean,
this is exactly what I'm going to talk about in the last. So this I wanted just to set the formalism and things by showing you how this quantum critical and classical critical behavior or thermal critical behavior are connected, and now I will talk to you about the inequivalence.
Okay. Yeah. Thanks.
Okay. If there are no other questions, I will want to use. I have still 23 minutes. No, 23, 25.
Yeah, 20 minutes.
Yeah, very good. So basically, in these last 20 minutes, I want to show you exactly what we were discussing 1 minute ago. So ensemble inequivalence. So ensemble inequivalence, Stefan has been talking to you about this property of fully connected systems, or not of fully, or long-range systems in general, but I guess he made you the example of fully connected system to have different descriptions with different thermodynamic ensembles. Now, the question is, how can we witness this in the quantum world? Well, in order to do this, I am thinking about a simplified, a very simple model. I don't know if Stefan has done you the classical version of it, but I'm going to use this model because it's very simple, both in the quantum and in the classical case. The Hamiltonian is similar to the one of before. So you have the ferromagnetic fully connected interaction, the transverse magnetic field. So these two pieces are exactly identical to before, but then we have a quartic fully connected interaction, okay? So basically what we added is a plaquette, if you want, an interaction between 4 spins. But also this interaction between 4 spins are global. So they are also, these are fully connected ones, and we can write them in terms of the global variable sigma z. So in some sense, these two guys, they work in the same team. So they both want to be the system to be ferromagnetic. They both want to spins to align along sigma z. It's just that they want it in different way because this is a power square and this is a power to the 4th. And they both have to fight against this sigma x, which wants to align their spins to the magnetic field. Very good. I have already laid out the theoretical part, so you need to just reapply what we just said before. We take the Hamiltonian of before, and we take the Hamiltonian I said, and we rewrite it in the global variables of before. The first part is exactly identical, and then we have the extra mz to the 4th term, so we have the extra term. And these are still the global interactions that I told you about. And I want, again, to compute the partition function, but now since I want to talk about inequivalence, okay, I want to talk about 2 different kind of partition function. One is the canonical one, the one that I have been describing before, is the trace of the Boltzmann weight. And the other one is the micro-canonical partition function. I know it's not so common. It's not so common to talk about a micro-canonical partition function in the quantum world, but we can do that. And the micro-canonical partition function will be just the trace of the delta function of phi minus the Hamiltonian. Now we need to solve for these two quantities. Using the same approach of before would be a bit lengthy, because you see this approach was very formal, very useful, but a bit complicated. I'm going to do something a bit simpler. I'm going to basically take the coherent state representation and try to make this a classical summation. And this is more heuristic, it's not so formal, but it still works. So basically, instead of calculating when I want to calculate the trace of e to the minus beta h, we know that we only have global operators. And so we just use the representation of the coherent states that I gave you before. So we use the coherent state representation in here, and we try to do the trace along these coherent states. So the trace splits up in this way. We have to consider all quantum numbers mz between minus s and s, okay, where s is the modulus of the spin. And then we have to sum over all possible modules of the spin from basically 1/2 to n, because there are n spins, and when you do the Clebsch-Gordon combination of all these possible spins, we get all possible moduli. So we have to do this classical summation. This is exactly the same as taking this e to the minus beta h and just sandwich to and we sandwich coherent states on the right and on the left. This looks much more simple than what I have done before, because I am immediately, instead of having infinitely many summation, one for each Trotter slice, I only do a single summation for coherent states on the left and on the right. Obviously, I have to pay a price. And the price I have to pay is that I have to count all possible multiplicities. So I have to count how many coherent states with a fixed spin modulus are given a lattice size n. So this is what I have to count. I have a lattice with n spins. I know that the total spin is a sum over all spins, and I have to count in how many ways I can sum up the spins in order to get a total spin of modulus s. So now it's become a little bit of a combinatorial game. So I have to account for the GS, which I didn't have before. If you remember, I didn't have the GS before, because before I used the trick to introduce the order parameter with the delta function, which looked a bit more formal and complicated, but it allowed me to skip this passage of calculating the degeneracies. But now I have to calculate these degeneracies, and we will see that one can kind of do this. The same procedure exactly will apply to the micro-canonical ensemble. To the micro-canonical ensemble, we have to do the same procedure. We sandwich on the left and on the right coherent states, and we obtain that this is a summation over classical values mz from minus s to s and summation over classical values of s, but we have to account for the multiplicity of s. And the Hamiltonian h in both cases depend only on s, z, and s. So this is kind of true. Very good. So how do we count the multiplicities? So, well, that's not so easy to be made. Basically, we need to do the calculation as I outlined here. So this number of multiplicities, it should be the Newton coefficients. So it's kind of an annoying combinatorial problem. What's important for us anyway is the thermodynamic limit. And so this is good for us because, and this is not even approximated, you see, because basically we know that S it's contained between 0 and n alpha, when n is the size of the system. So, but we already know from before that in the end, we want to take the thermodynamic limit n to infinity. And in the limit n to infinity, we can make an approximation. And when we make this approximation, we obtain just this a simple Stirling formula. That's the one obtained here. Okay. And S is small s is just big S divided by M. Okay. So small s is big S divided by M. And so what I am just saying is that in this more heuristic approach, one has to compute the multiplicity. The multiplicity are equal to this value. These are the Newton coefficients. It's a combinatorial problem. I don't want to talk about this too much. But in the thermodynamic limit, we can approximate the GS with this simple formula. And this approximation is kind of the counterpart of the approximation we did before in here, where we take the saddle point at large n. So here it was a bit more formal, and at large n, we just showed that it's only the saddle point contribution dominates. And in here, more heuristically, we say, okay, in the large n limit, we can approximate this degeneracy just by the Stirling approximation. And when we do this, we basically obtain formulas like this, which are, again, in the form of a saddle point, because what we have done, we have taken this GS, we have taken out an N out of S, and we made this a small s, and in the large N limit, instead of a summation over S, we can do an integral over small s from 0 to 1, and we get that basically the integral of the summation over mz becomes an integral over theta and phi, and we get an equation like this for our partition function, and a similar equation for the micro-canonical partition function omega epsilon, which gives us this result. You see, again, the analogy with before. Even in this case, we have integrals. We have to integrate over some variables to obtain the partition function, but the integrand is of exponential form, and the exponent is multiplied by n. So this again suggests that in the thermodynamic limit, n acts as a control parameter for our system, and we can use saddle point approximation. So we can use saddle point approximation to evaluate these two integrals, otherwise we cannot evaluate analytically. And another thing, sorry.
So this, so can you just go back to the previous slide? I mean,
yeah.
No, the previous one maybe. Yeah. So so there are two summations. So the summation over mz somehow became a surface integral. Is that right?
Yeah, exactly. Because a surface integral over theta and phi. This I will explain. This is what I will explain very clearly during the tutorial.
Okay. Okay. Thanks.
So very clearly you will see. So basically, but it's not so. In some sense, it's not so hard to be seen. Unfortunately, I didn't put a slide, but okay, we can discuss this during the tutorials. It's a very simple thing. It's just that basically when you do this procedure of taking the large m, which is also the large n limit, because m is just n half. When you took the large n limit, you can approximate the spin as a classical variable. This is due to the saddle point. And so it's more convenient to parameterize the spin as angles, no? Because normally you don't parameterize the spin as a quantum mz. In the classical world, you parameterize it by an angle. And so this is why I write it in this way, but I will show you how this is obtained. Or not how it is obtained in this way, but in a different way, how this comes up. Okay, so basically, so the summation over S transforms in this, and the summation over mz transforms into these integrals over the faces, which are nothing but the angle that the spin makes with the z direction. So this mz. And the same, of course, for the omega epsilon h, which is the micro-canonical partition function. So you see, basically, I just explained you how to do the canonical one, and the micro-canonical always follows, because the micro-canonical and the canonical are kind of the same thing. The only difference is that here you have an exponential, here you have a delta function, but in order to solve the delta function, you use the usual trick. You use the usual trick. And the usual trick is that you take the delta function as an integral of an exponential. And so you do the calculation exactly in the same way in the micro-canonical case. The only additional thing is that in the canonical case, you have an additional integration over lambda, which is the additional integration that comes from the fact that you have transformed the delta function into an integral of an exponential. Okay, so that's done. And if you look into these two guys, the free energies, you get exactly these expressions. And these expressions are, they contain nothing but the average of the Hamiltonian, which is this guy in here, plus the contribution from the degeneracies. So you see, the free energy contains both the average of the Hamiltonian, this term here, and the contribution from the degeneracies. This is for the free energy. And it's kind of the same thing happens for the, so, and this is the energy of the system. So this is just the average of the Hamiltonian, and this is the free energy. But in the limit t equals 0, as you expect, this contribution from the degeneracies washes away, and the free energy, this F in here, becomes just the average of the Hamiltonian. And then basically, we are a little bit in trouble, because you see, the canonical formulation will be to make, the canonical formulation wants you to make the minimum of the free energy, because you take n to infinity and you have to make the saddle point, and you have to make the minimum of this free energy. The micro-canonical formulation, on the other hand, it doesn't want you to minimize the free energy, but it wants to minimize you the epsilon minus the free energy. So it wants you to find the surfaces of fixed free energy, where epsilon, I remind you, epsilon is E over N. So it's just a number that you decide. So basically, the situation is kind of different for finite temperatures. It's different for finite temperatures, but at 0 temperature, the free energy becomes the energy. And this epsilon here becomes the ground state energy. And so basically, minimizing this F, or minimizing F minus epsilon, it becomes the same thing, because the free energy there is no difference between free energy and energy, because the contribution from the entropy that was this degeneracy has been washed away. And on the other end, finding the minimum of this energy is the same as finding the ground state, because the ground state and the minimum are the same thing at 0 temperature. And so somehow the two approaches, they give the same phase diagram for the model. And the same phase diagram is the one that I display in here. So there is no ensemble inequivalence at 0 temperature exactly. Because at 0 temperature exactly, the phase diagram is the one of a tricritical point. So it's an interesting phase diagram, because you have the competition between the quartic K and the quadratic J, end of the H, of course. And when you fix k to 1, when k is equal to 1, so the quartic term is 1, you get that as a function of j and h, you get this phase diagram. You have a ferromagnetic and a paramagnet, so the phases are just 2, because as I told you, both j and k, they want a ferromagnet to occur. But for large j, for large j, the transition is of second order. And for small j, the transition is of first order. Why? Because for small j, it's not j that drives the transition, but it's k, it's the quartic term. And it's the point that separates the second order line from the first order line, it's a tricritical point. It's a tricritical point where the derivative of the free energy is discontinuous at the third order. So this point separates these two lines. And you have at the tricritical point, basically, a free energy that looks like this. A free energy that you remember in this case is just the energy, because at 0 temperature, the free energy is washed away. So there is no real ensemble inequivalence in the quantum phase transition world, but this you can see it from the beginning, because in the quantum phase transition, when you take t formally, when you take t going to 0, basically this already tells you that you are selecting only the minimal. You can do kind of some fake heuristics at the point, and you say that in the t equal to 0 limit, beta goes to infinity, and you are selecting only ground state contribution from H, only the place where H is minimum. But this is the same as in the micro-canonical ensemble, as to us that this E is the minimum E. So basically, you see in the t equal to 0 limit, the exponential works as a delta function of the ground state. So there is no distinction between two. So there is a formal difference between these two, but physically, these two are telling you the same thing. In the micro-canonical, if you want the ground state, you have to place E to be the ground state energy. In the canonical, the ground state at finite temperature is not the ground state of the micro-canonical, but at 0 temperature, they are the same. And so there cannot be any inequivalence. However, there is an inequivalence when you go to finite temperature corrections. And this is what you have seen also with Stefano. The calculations is kind of involved. I don't want to show you because it's really complicated. But what you can see is that if you take leading order temperature corrections along these lines, and you deform the lines by a small finite temperature, these points moves in two different directions if you represent it in the canonical or in the micro-canonical ensemble. Indeed, in the canonical ensemble, the location of this point, this is the location. So these two numbers give you the location of the tricritical point. No? This point it's located by satisfying both this equation at the same point, with k equal to 1, obviously, with k equal to 1. They are the same when beta is equal to 0. These corrections vanishes, and you have this relation to be 1 altogether. But when the temperature is finite, you see that this is the same. So the second order line moves in the same way, but the tricritical point moves in two different ways. So basically, when you do finite temperature corrections, this line shifts a bit the same way in the canonical and micro-canonical, but in the micro-canonical, this point goes further up the line, and in the canonical, it goes further down the line. And this you see from the fact that these two signs are different. So the bottom line of my talk is that there is no ensemble inequivalence in the full quantum limit. So in at 0 temperature, canonical and micro-canonical analysis are exactly the same for the reason I have told you before. But when you compute leading order corrections in finite temperature for the quantum model, also in the quantum model, you see ensemble inequivalence, and this ensemble inequivalence is similar to what happens in the classical case that you have been studying during the week. Okay, so thank you very much. And this is all what I wanted to say for now.
Okay. Yeah, any questions?
In the last plot that you showed, shouldn't there be like, there should be a discontinuity according to the last slide, right?
Which, sorry.
What does the different values of JTCP means?
I know, so basically, so this plot is only at 0 temperature. So when beta is equal to infinity. So when beta equal to infinity, there is no discontinuity, you see? There is, so when beta is equal to infinity, this correction, they go to 0. So at 0 temperature, you see this plot. At finite temperature, unfortunately, I was unable to make a figure that was decent enough for this. At finite temperature, what you see is that, okay, the line moves a bit, okay? And it moves in the same direction, both for the canonical and micro-canonical. Okay, at finite temperature, you will see this line moving a bit. But in the canonical, this point will move backwards. And in micro-canonical, it will move upwards. Okay? So this is ensemble inequivalence in the quantum world. So at the quantum phase transition, the ensemble are perfectly equivalent. But when you compute finite temporal corrections, you see that the critical point moves into 2 different directions. But this is not visible in the figure. The figure is done only for t equals 0, because otherwise it would be a 3-dimensional figure. It would be very hard to be seen.
Okay, so if there are no other questions, maybe we'll break now for coffee.